According to NEC 250.24a, equipment grounding conductors must be connected to the grounding terminal or bar within the same enclosure or raceway where the circuit originates. Therefore, grounds passing through one section of a panel board must terminate in the same section where they are pulled into. Now let's discuss the neutral conductors. NEC 220.85 states that neutral conductors must terminate in the same enclosure or at the same termination point as the circuit breaker that supplies it. This means that neutrals must pass through the panel board and terminate in the same section as the circuit breaker. There is an exception for interconnection. NEC 312.8d provides an exception for panel boards that are interconnected using an approved method. Using this exception, it is permissible to pass ground and neutral conductors through a section of the panel board and terminate them in another section, but the interconnections must be made in accordance with the equipment manufacturer's instructions. NEC 220.85 is a specific code reference for the requirement that neutrals must pass through and terminate in the same can as the circuit breaker. Let's delve a little deeper into the specifics of each code section. Starting with NEC 250.24a, this section is crucial for ensuring electrical safety by establishing a low impedance path for fault current to return to the source. This path allows overcurrent protective devices to operate and clear the fault, minimizing the risk of electrical shock or fire. The term equipment grounding conductor refers to the conductive path installed to connect normally non-current carrying metal parts of equipment to the system grounded conductor, the grounding electrode conductor, or both. This conductor is essential for providing a safe path for fault currents. The grounding terminal or bar within the enclosure is the designated point where all equipment grounding conductors are connected. This terminal is typically bonded to the enclosure itself, creating a direct connection to ground. The phrase same enclosure or raceway where the circuit originates emphasizes that the grounding conductor must be connected to ground within the same physical space as the circuit's power source. This minimizes the length of the fault current path, reducing impedance and ensuring effective fault clearing. Moving on to NEC 220.85, this section addresses the proper termination of neutral conductors in relation to their corresponding circuit breakers. The neutral conductor, also known as the identified conductor, carries the unbalanced current from the load back to the source. Proper termination of the neutral conductor is essential for maintaining voltage balance and preventing excessive neutral current, which can lead to overheating and equipment damage. The phrase same enclosure means that the neutral conductor must terminate within the same physical enclosure as the circuit breaker that supplies the load. This ensures that the neutral conductor is properly associated with its corresponding circuit breaker and minimizes the risk of improper connections. The phrase same termination point refers to the specific location within the enclosure where the neutral conductor is connected. This termination point is typically a neutral bar or terminal block that is specifically designed for this purpose. The term circuit breaker that supplies it reinforces the importance of connecting the neutral conductor to the circuit breaker that provides power to the load. This ensures that the neutral conductor is properly sized and protected by the circuit breaker. Now let's explore NEC 312.8d, which provides an exception for interconnected panel boards. This exception recognizes that in certain installations, it may be necessary to pass conductors through one section of a panel board to reach another section. The phrase panel boards that are interconnected refers to panel boards that are physically connected to each other, typically through a raceway or other approved means. This interconnection allows for the sharing of conductors between the panel boards. The term approved method signifies that the interconnection must be made in accordance with industry standards and best practices. This typically involves using listed and labeled components and following the manufacturer's instructions. The phrase equipment manufacturer's instructions emphasizes the importance of following the manufacturer's recommendations for interconnecting panel boards. These instructions typically provide specific guidance on conductor sizing, termination methods, and other critical details. It is important to remember that NEC 110.3b requires that all equipment must be installed and used in accordance with the manufacturer's instructions and listing requirements. Failing to adhere to these instructions can result in code violations, equipment damage, and safety hazards. In summary, understanding and complying with NEC 250.24a, 220.85, and 312.8d is essential for ensuring the safe and reliable operation of electrical systems. By properly terminating grounding and neutral conductors in panel boards, you can minimize the risk of electrical shock, fire, and equipment damage. Remember that local codes and regulations may vary, so it is always advisable to consult with a qualified electrician or electrical inspector to ensure compliance with all applicable requirements. Now let us consider the application of these rules in different scenarios. Firstly, consider a scenario where a circuit originates in the left section of the panel board and needs to supply power to a load that is physically located closer to the right section of the panel board. In this case, the equipment grounding conductor for that circuit must terminate in the grounding bar within the left section of the panel board, even though the load it serves is closer to the right section. The neutral conductor, however, must pass through the left section and terminate in the neutral bar within the right section alongside the circuit breaker that supplies the power to the load. Secondly, let's consider a situation where two panel boards are interconnected via a short length of conduit. If the installation meets the requirements outlined in NEC 312.8d and the manufacturer's instructions, it would be permissible to run both the grounding and neutral conductors from a circuit originating in one panel board through the conduit and terminate them in the other panel board. This exception is particularly useful in situations where it is more practical or convenient to terminate the conductors in a different panel board than where the circuit originates. However, it is crucial to ensure that the interconnection is properly sized and installed to maintain the integrity of the grounding and neutral paths. Thirdly, let's examine a scenario involving isolated ground circuits. Isolated ground circuits are often used in sensitive electronic equipment installations to minimize electrical noise and interference. In these circuits, the equipment grounding conductor is intentionally isolated from the normal equipment grounding system to prevent unwanted currents from flowing through the ground path. While the general rule requires equipment grounding conductors to terminate in the same enclosure as the circuit originates, special considerations apply to isolated ground circuits. The NEC provides specific guidelines for the installation of isolated ground circuits, including requirements for the isolation of the grounding conductor and the use of approved grounding methods. In all cases, it is essential to carefully review the NEC and any applicable local codes to ensure compliance with all requirements. Additionally, consulting with a qualified electrician or electrical inspector can provide valuable guidance and ensure that the installation is safe and reliable. Let's discuss some common misconceptions about grounding and neutral conductors in panel boards. One common misconception is that grounding and neutral conductors can be treated interchangeably. While both grounding and neutral conductors play important roles in electrical systems, they serve different purposes and have different requirements. Grounding conductors provide a low impedance path for fault current to return to the source, while neutral conductors carry the unbalanced current from the load back to the source. Another common misconception is that the size of the grounding conductor can be reduced to save money. The NEC specifies minimum sizes for grounding conductors based on the size of the circuit conductors. Reducing the size of the grounding conductor can compromise the safety of the electrical system and increase the risk of electrical shock or fire. A third misconception is that it is acceptable to share a neutral conductor between multiple circuits. While multi-wire branch circuits are permitted under certain conditions, the NEC has specific requirements for sharing neutral conductors to prevent overloading and voltage imbalance. Sharing a neutral conductor without proper consideration can create safety hazards and damage equipment. It is always important to consult the NEC and follow best practices when working with grounding and neutral conductors and panel boards. Now let's discuss some practical tips for working with grounding and neutral conductors and panel boards. Firstly, always disconnect power to the panel board before working on any electrical connections. This is the most important safety precaution to prevent electrical shock. Secondly, use appropriate tools and equipment for the job. This includes insulated screwdrivers, wire strippers, and crimping tools. Thirdly, carefully identify and label all conductors before making any connections. This will help to prevent errors and ensure that the installation is correct. Fourthly, tighten all connections to the proper torque specifications. Loose connections can create heat and cause electrical problems. Fifthly, inspect all connections after they are made to ensure that they are secure and properly insulated. Sixthly, use the multimeter to verify the continuity of the grounding and neutral conductors. This will help to identify any broken or loose connections. Finally, document all work that is performed. This will provide a record of the installation and make it easier to troubleshoot any problems in the future. Following these practical tips can help to ensure that the installation of grounding and neutral conductors in panel boards is safe, reliable, and compliant with the NEC. Let's also consider the impact of harmonics on neutral conductors. Harmonics are non-sinusoidal waveforms that can be generated by electronic devices such as computers, variable frequency drives, and LED lighting. These harmonics can cause excessive current to flow in the neutral conductor, which can lead to overheating and equipment damage. To mitigate the effects of harmonics on neutral conductors, it is important to use oversized neutral conductors, install harmonic filters, and use balanced loads. The NEC provides specific guidelines for sizing neutral conductors in systems with harmonic currents. Consulting with a qualified electrical engineer can help to ensure that the neutral conductors are properly sized and protected in these types of systems. Now let's discuss the importance of bonding in panel boards. Bonding is the process of connecting all non-current carrying metal parts of the electrical system together to create a low impedance path for fault current to return to the source. Proper bonding is essential for ensuring electrical safety and preventing electrical shock. The NEC provides specific requirements for bonding in panel boards, including the use of bonding jumpers, bonding bushings, and grounding electrodes. It is important to follow these requirements carefully to ensure that the bonding system is effective. In addition to the NEC requirements, many manufacturers provide specific instructions for bonding their equipment. These instructions should be followed carefully to ensure that the equipment is properly bonded. Failing to properly bond equipment can create safety hazards and violate code requirements. Let's also consider the use of surge protective devices in panel boards. Surge protective devices, or SPDs, are designed to protect electrical equipment from voltage surges caused by lightning strikes, utility switching, and other events. SPD can be installed in panel boards to provide protection for the entire electrical system. The NEC provides specific requirements for the installation of SPD, including requirements for the location, wiring, and grounding of the devices. It is important to follow these requirements carefully to ensure that the SPD are effective and do not create any safety hazards. In addition to the NEC requirements, many manufacturers provide specific instructions for installing their SPD. These instructions should be followed carefully to ensure that the devices are properly installed and will function as intended. Finally, let's discuss the importance of regular maintenance of panel boards. Regular maintenance can help to identify and correct any problems before they become serious. Maintenance tasks should include inspecting all connections for tightness, checking for signs of corrosion or damage, and testing the operation of circuit breakers and other protective devices. The NEC recommends that panel boards be inspected and maintained on a regular basis, typically at least once a year. In addition to regular maintenance, it is important to keep panel boards clean and free of dust and debris. Dust and debris can accumulate on electrical components and cause them to overheat or malfunction. Following a regular maintenance schedule can help to ensure that panel boards are operating safely and reliably. Let's delve into more specific details about conductor sizing and ampacity. The National Electrical Code, or NEC, provides tables and guidelines for determining the appropriate size of conductors based on the ampacity, or current carrying capacity, required for a given circuit. Ampacity is determined by factors such as the load connected to the circuit, the ambient temperature, and the number of conductors bundled together. NEC Table 310.15b16, formerly known as Table 310.16, is a critical reference point. This table lists the allowable ampacities of insulated conductors rated up to 2000 volts based on the conductor's insulation type and its operating temperature. For example, a copper conductor with THHN insulation, which is commonly used, has a higher ampacity rating than a conductor with TW insulation, which has a lower temperature rating. The NEC also includes adjustment factors that must be applied when multiple current-carrying conductors are bundled together in a raceway or cable. These adjustment factors reduce the allowable ampacity of each conductor to account for the increased heat generated by the group of conductors. For example, if there are 4 to 6 current-carrying conductors in a raceway, the allowable ampacity of each conductor must be reduced to 80% of the value listed in Table 310.15b16. Furthermore, the NEC requires that conductors be protected against overcurrent by circuit breakers or fuses. The overcurrent protection device must be sized to protect the conductor based on its ampacity. For example, a 12 American wire gauge or AUG copper conductor with THHN insulation has an ampacity of 20 amps, so it must be protected by a 20 amp circuit breaker or fuse. It is essential to consult the NEC and follow all applicable requirements when selecting and installing conductors to ensure that the electrical system is safe and reliable. Now let's discuss the different types of grounding electrodes. A grounding electrode is a conducting object that establishes a connection to the earth, providing a path for fault current to return to the source. The NEC recognizes several different types of grounding electrodes, each with its own requirements for installation and sizing. One common type of grounding electrode is a ground rod. Ground rods are typically made of copper or copper-clad steel and are driven into the earth to a minimum depth of 8 feet. The NEC requires that ground rods be at least 8 feet long and 1/2 inch in diameter. Another type of grounding electrode is a ground plate. Ground plates are typically made of copper or galvanized steel and are buried in the earth to a minimum depth of 30 inches. The NEC requires that ground plates have a surface area of at least 2 square feet. A third type of grounding electrode is a concrete encased electrode, also known as a UFA ground. A concrete encased electrode consists of at least 20 feet of bare copper conductor that is encased in concrete that is in direct contact with the earth. The NEC requires that the concrete be at least 2 inches thick and that the conductor be at least 4 AWG in size. In addition to these common types of grounding electrodes, the NEC also recognizes other types of electrodes, such as metal underground water pipes and metal building frames. The selection of the appropriate type of grounding electrode depends on factors such as soil conditions, the size of the electrical system, and local code requirements. It is always advisable to consult with a qualified electrician or electrical inspector to determine the best type of grounding electrode for a particular application. Now let's consider the use of ground fault circuit interrupters, or GFCIs. GFCIs are life-saving devices that are designed to protect people from electrical shock. GFCIs work by monitoring the current flowing in a circuit and quickly interrupting the power if a ground fault is detected. A ground fault occurs when current flows through an unintended path, such as through a person's body. GFCIs are required in many locations throughout the home, including bathrooms, kitchens, and outdoor areas. The NEC provides specific requirements for the installation of GFCIs, including requirements for the location, wiring, and testing of the devices. It is important to follow these requirements carefully to ensure that the GFCIs are effective and do not create any safety hazard. In addition to the NEC requirements, many manufacturers provide specific instructions for installing the GFCIs. These instructions should be followed carefully to ensure that the devices are properly installed and will function as intended. Testing GFCIs regularly is essential to ensure that they are working properly. GFCIs should be tested at least once a month by pressing the test button on the device. If the GFCI does not trip when the test button is pressed, it should be replaced immediately. Now let's explore the concept of selective coordination in electrical systems. Selective coordination is a design principle that ensures that only the overcurrent protective device closest to a fault will trip, minimizing the impact of the fault on the rest of the electrical system. Selective coordination is particularly important in critical facilities such as hospitals, data centers, and emergency response centers, where a disruption of power can have serious consequences. The NEC provides requirements for selective coordination in certain types of electrical systems, including emergency systems, and legally requires standby systems. Achieving selective coordination requires careful selection and coordination of overcurrent protective devices, such as circuit breakers and fuses. Time current curves are used to analyze the performance of overcurrent protective devices and ensure that they are properly coordinated. Time current curves show the amount of time it takes for an overcurrent protective device to trip at different levels of current. By comparing the time current curves of different overcurrent protective devices, it is possible to determine whether they are selectively coordinated. In addition to the NEC requirements, many manufacturers provide software and tools to assist in the design of selectively coordinated electrical systems. Consulting with a qualified electrical engineer is essential to ensure that selective coordination is properly implemented in an electrical system. Now let's discuss the importance of arc flash hazard analysis. Arc flash is a dangerous phenomenon that can occur when a short circuit creates an electrical arc. Arc flashes can generate intense heat, pressure, and light, which can cause serious injuries or even death. An arc flash hazard analysis is a study that is conducted to determine the potential arc flash hazards in an electrical system. The analysis identifies the locations where arc flashes are likely to occur and calculates the potential arc flash incident energy at each location. The results of the arc flash hazard analysis are used to determine the appropriate personal protective equipment, or PPE, that workers must wear when working on or near energized electrical equipment. The NEC requires that an arc flash hazard analysis be performed for certain types of electrical systems. OSHA also has regulations regarding arc flash safety. The IE 1584 standard provides guidance on how to perform an arc flash hazard analysis. Conducting an arc flash hazard analysis is essential to ensure the safety of workers who are working on or near energized electrical equipment. Now let's consider the topic of energy efficiency in electrical systems. Energy efficiency is the practice of using less energy to perform the same task. Improving energy efficiency can save money on energy bills, reduce greenhouse gas emissions, and conserve natural resources. There are many ways to improve energy efficiency in electrical systems, including using energy-efficient lighting, installing variable frequency drives on motors, and optimizing the operation of HVAC systems. The NEC includes requirements for energy efficiency in certain types of electrical systems. The International Energy Conservation Code, or IC, provides additional requirements for energy efficiency in buildings. Utility companies often offer rebates and incentives for customers who install energy-efficient equipment. Conducting an energy audit can help to identify opportunities to improve energy efficiency in an electrical system. Now, let's discuss the use of renewable energy sources in electrical systems. Renewable energy sources, such as solar, wind, and hydropower, are becoming increasingly popular as a way to reduce reliance on fossil fuels and mitigate climate change. The NEC includes requirements for the installation of renewable energy systems, including requirements for wiring, grounding, and overcurrent protection. The IE 1547 standard provides guidance on the interconnection of distributed generation resources, such as renewable energy systems, to the electrical grid. Local permitting and inspection requirements may also apply to the installation of renewable energy systems. Consulting with a qualified electrical engineer or contractor is essential to ensure that renewable energy systems are safely and properly installed. Now let's explore the topic of electrical system grounding and bonding for sensitive electronic equipment. Sensitive electronic equipment, such as computers, servers, and medical devices, can be susceptible to damage or malfunction from electrical noise and transients. Proper grounding and bonding are essential to protect sensitive electronic equipment from these problems. The NEC provides specific requirements for grounding and bonding in areas where sensitive electronic equipment is used. Isolated ground receptacles are often used to provide a dedicated grounding path for sensitive electronic equipment. Surge protective devices, or SPDs, are also used to protect sensitive electronic equipment from voltage surges. Shielded cables and raceways can be used to reduce electrical noise. Conducting a site survey to assess the grounding and bonding system is essential to ensure that it is adequate for the sensitive electronic equipment being used. Now, let's consider the topic of electrical safety in healthcare facilities. Healthcare facilities have unique electrical safety requirements due to the presence of patients who may be particularly vulnerable to electrical shock. The NEC includes specific requirements for electrical systems in healthcare facilities, including requirements for essential electrical systems, patient care areas, and wet locations. Essential electrical systems provide backup power to critical equipment in the event of a power outage. Patient care areas have stringent requirements for grounding and bonding to minimize the risk of electrical shock. Wet locations, such as operating rooms and hydrotherapy areas, have additional requirements for ground fault protection. Healthcare facilities must have a comprehensive electrical safety program in place to ensure the safety of patients, staff, and visitors. Now let's explore the topic of electrical system design for data centers. Data centers are facilities that house large numbers of servers and other computing equipment. These facilities have unique electrical system requirements due to the high density of equipment and the need for reliable power. The NEC includes specific requirements for electrical systems in data centers, including requirements for uninterruptible power supplies, or UPSs, power distribution units, or PDUs, and cooling systems. Uninterruptible power supplies provide backup power to the servers in the event of a power outage. Power distribution units distribute power to the servers and other equipment in the data center. Cooling systems are essential to remove the heat generated by the servers. Data centers must have a comprehensive electrical system design that takes into account the specific needs of the facility. Now, let's consider the topic of electrical safety for industrial facilities. Industrial facilities have unique electrical safety requirements due to the presence of hazardous materials, heavy machinery, and potentially explosive atmospheres. The NEC includes specific requirements for electrical systems in industrial facilities, including requirements for hazardous locations, motor control centers, and grounding and bonding. Hazardous locations are areas where flammable gases, vapors, or dust may be present. Motor control centers are used to control and protect electric motors. Grounding and bonding are essential to prevent electrical shock and minimize the risk of fire or explosion. Industrial facilities must have a comprehensive electrical safety program in place to ensure the safety of workers and prevent accidents. Now let's talk about electrical systems in agricultural buildings. Agricultural buildings, such as barns and poultry houses, have unique electrical system requirements due to the presence of livestock, moisture, and corrosive materials. The NEC includes specific requirements for electrical systems in agricultural buildings, including requirements for wiring methods, grounding and bonding, and overcurrent protection. Wiring methods must be suitable for the wet and corrosive environment. Grounding and bonding are essential to prevent electrical shock to livestock and humans. Overcurrent protection must be adequate to protect the electrical system from overloads and short circuits. Agricultural buildings must have a comprehensive electrical safety program in place to ensure the safety of livestock and humans. Lastly, consider the topic of electrical inspections and permits. Electrical inspections are conducted by qualified inspectors to ensure that electrical installations comply with the NEC and other applicable codes. Permits are typically required for new electrical installations, alterations, and repairs. The permitting process ensures that electrical work is performed by qualified individuals and that it meets the required standards. Electrical inspections help to identify and correct any potential safety hazards. It is important to comply with all applicable electrical codes and regulations to ensure the safety of people and property.